Hi, I was here about to cook something when I got distracted by, well, you can see, and it made my mind start wandering, and it reminded me of something that we've been developing at my work. So I work in a team that provides computing resources to our university. So in particular, high-performance computing resources. So basically the big computers people use when they need to do large-scale computing simulations, data analysis, things like that. So people sometimes come to us and ask, oh, can we use your resources? And we say yes. And then they're like, oh, okay, they start using them. And it turns out that their work isn't actually running faster there. So why is that? Shouldn't the bigger computer be faster? So in some ways, yes, but you have to know how to use it. And that's what this metaphor is about. So what I'm going to do is explain the basics of the metaphor, and in future videos we'll go into details about some of the different parts. So let's see, what comes first? First is the processors. So basically the things that's doing all of the actual computing. So processors these days tend to have multiple computing cores inside of them. So in that case, the stove has 4 burners in it. In order to make full use of the stove, I need to be able to use all of these different burners at the same time. And to use the burners, it's a process or thread of a process. So basically, that's an independent thing that's being executed and doing some task. So you have to have one processor thread for each task that's executing in order to use the burner. Okay. What about this stove here versus this 1.8 kilowatt induction burner? This is like a laptop GPU in this metaphor versus this desktop CPU. So is the stove much more powerful than the hot plate? So from the best I can tell by looking up the powers of this, no, not really. So each individual burner here is about as powerful as this. Maybe some are a little bit more powerful, but I mean, it's not like an order of magnitude or anything. So the only way that the bigger processor is useful is by being able to use all the cores at once. Next up, we have some things like graphical processing units, or GPUs, which maybe I've inserted into a picture here. So this is a food truck that I saw once, and from the best I can tell, it can cook several hundred chickens at the same time. So graphical processing units are good when you want to do the same thing many times. So you can do an incredible amount of work that way. But if the work isn't what the GPU does, then it's not the right thing. For example, if I want to make pasta, this GPU won't let me do anything at all. Luckily, GPUs are good for doing linear algebra, and that's essentially what a lot of science can be programmed as. Okay, what comes next? We have things like data. So data is the ingredients. So if we can't get the data to the stove, the processor, then there's not much point here. And on something like a desktop computer in this kitchen, moving the data around isn't really a problem. But once you get to a big server computer that has many things going on at the same time, then you have to start thinking about this even more. Sometimes the data transfer is what's slowing everything down. Okay, no. The distraction is continuing. Okay, so the data is stored in memory. So memory is basically our working space. So ingredients generally go to memory and then they can be used in the processor. There's different types of memory. For example, a processor cache is really close to the processor on the same chip. And the ingredients and data can be moved back and forth very quickly. Other things like the main memory of the computer is slightly farther away, and it takes slightly longer to move things back and forth, but it's larger. next up, we have things like storage. So storage is where bulk ingredients can be held and more long-term than the memory. And again, there's different types of storage. For example, there's storage that's right nearby, and that's the fastest to move things back and forth. This might be, for example, a SSD drive in the cluster on one of the nodes that has the processor. But again, there's different types of storage. For example, the refrigerator is slightly slower to move things back and forth from, but it holds things for a longer term. This might be a hard drive. And then finally, there's other storage. For example, I have some bulk storage of goods further away. That's even larger but slower to access. Okay, next up we have things like code. So code is the recipes we use for cooking. Whenever you started to learn programming, you probably learned that computers are very strict and picky. They do exactly what you say, no more, no less. That's the same in the cluster computers, but it gets even it gets different because you have to coordinate different things. We'll talk about that soon. Okay, so next up, if we want to upgrade from this kitchen, we might move to an industrial kitchen like we might see in a restaurant. So fundamentally, it looks pretty similar to what we have here. There is a stove, there's memory, there's storage. All of it's slightly bigger, and there might be more of them. But fundamentally, you can use the same recipes there. But if I go rent an industrial kitchen myself, am I going to be able to cook a lot more or a lot faster? Probably not in the end. I mean, the stove might be slightly more powerful, but it's not fundamentally different than what we see here. The way that a restaurant kitchen can cook so much food is it has multiple people working there, multiple cooks that are the processes that are able to coordinate across each other. If we go one step up, we have the computer cluster, the high-performance computing cluster. So people these days don't make clusters by getting really big computers, but they take powerful server-grade computers like this kitchen in the restaurant, and they put them side by side, connected by a network. So that network can be used to send data between the different computers and to the large network-attached storage system. So in order to use these larger clusters, it's not just you take what you have and go there and suddenly you can cook a lot more food. You have to do a new kind of work and a new kind of programming. You have to tell your programs how to distribute its tasks across all these different stoves, across all these different kitchens, to move the data from the common storage to each kitchen, do the cooking, and recombine all the outputs to what you need. So just like the normal code has to be very strict and precise about what it does, whenever you're using the cluster, your code has to be very strict and precise about how to use these multiple resources together at the same time. So in essence, when you're using the cluster, you're not just cooking something, you're not just running your program, but you're becoming the manager of all the other cooks that are cooking things. You write scripts and you write code and so on that tells all the other code how to split up among things and work together. So in essence, it's a different kind of job. So maybe it's what you like. Maybe you'll find this really fun. Maybe you would like to just focus on your science and not worry about it. Well, that's where people like me come in. My team is around to help you use the cluster, even if you don't want to become the expert in the cluster yourself. So with that being said, hopefully this is a good basic introduction. There will be follow-ups where we go into other types of things. For example, how to cook things in parallel, or how memory and data storage hierarchy works, or how the resources are allocated, which will drill down into some of the more specialized topics here. But with that being said, now my distraction is, well, now it's coming back. But I will try to get back to my food. So talk to you later.